Hello all, welcome back to the another lecture. So in the previous lecture we have seen the single pulse test and double pulse test. Now we will see how to design the circuit of double pulse test. So my name is Ashish and let's get started with the lecture. So in this lecture we will see the first theory, how to design the double pulse test circuit, and after that we will solve one numerical problem on the same. So let's get started. So theory of double pulse test circuit. So let us get started. So we will see the theory first. Now this is the basic circuit of the double pulse test. So these are the key component which are shown here. So what are the different key components present here? One is a DC source. DC source is important. Second one is a bleeder resistance is available here. Then the capacitances are there. So two capacitances are there. One is the energy storage capacitance and another is a decoupling capacitor. Then my load inductor, that is very important because double pulse test is carried with the load inductor only. This theory we have covered in the previous class. So all these thing designing is very important, and this thing we will see in this lecture. So you just take the screenshot of this circuit, because we will design how to take value of DC source, what value of bleeder resistance we will take, what value of the different capacitances we will take. So all these things we will see in the theory first, right? So we will start with the one by one. So the first is as shown in the above figure. In addition to the power devices, the key component of the double pulse circuit include what? In load inductor is there, DC source is there, DC capacitance we have already seen. So including the energy storage capacitance and the decoupling capacitor. What is the importance of this two capacitances and all we will see. Then bleeder resistance, gate driver and short circuit protection, all these things are there, right? So we will start first with the load inductor. So how to choose the value of load inductor and all that we will see. So what is the purpose of this load inductor? This theory we have already covered in our previous class, but just in summary I have written down that the load inductor is used to establish the desired current during the first pulse and keep this current nearby constant during the subsequent turn on and turn off transient. Therefore, the selected load inductance L should be large enough to limit the inductive current variation, that is delta IL, during the switching transient. So we have to choose the value of inductance large enough such that the ripple in the current variation should not be too much, right? So this thing we have already seen in the theory. So what value of the inductor will take? So the formula for calculating the load inductance is L equals to VDC divided by K delta I into IL multiplied by TSW. Now the question is, what VDC we will take, what IL we will take. So when you buy any device, there is a mention that this is the VDC value, this is the minimum to maximum VDC you can use, and for the IL also this is the minimum to maximum current that device can withstand. Okay. So for calculation of the inductance, whether we will take maximum current or maximum voltage or minimum voltage and minimum current, what combination we will take, I will tell you later. But as of now, you just know that this is the formula which you have to use. Now, what is this K delta I? K delta I represents the current variation percentage during the switching transient. So you can consider 2%, 3% variation. So that is fine, right? So this is the about the load inductance design. Okay, so you have to know what is the purpose of load inductance and what is the formula for calculating the load inductance. Okay, once you know this, so what is value of the VDC minimum or maximum we will take, that I will tell you in the numerical afterward. So the second component is the DC source. What is the value of DC source we should take? So some theory is there, from that you will understand that what value of VDC we should take. So when we have device, we come to know that this device is operate for this much of voltage and this much of current, right? So now what is written down here? The DC source is used to establish the DC bus voltage. What is the bus voltage? The capacitance bus voltage. Thus, its rated voltage should be higher than the maximum DC bus voltage needed for the device characterization. So whatever the device maximum temperature, we should take that or bit of higher than this, so that we can maintain this maximum DC bus voltage needed for the device. Second thing, on the other hand, the current rating of the DC source should be much lower than the maximum characterization current for the device under test. So in the device they will mention that this is the maximum current requirement and this is the minimum current requirement. So what is my requirement for the DC source? So I should be take DC source such that it is much lower than the maximum characterization current for the device under test, since most of the energy for double pulse test come from the DC capacitor bank. So DC capacitor bank, this is the bus voltage which we will given to the our device. Okay, so DC how to design the capacitance we will see in the next part. But so maximum most of the energy of the DPT comes from the DC capacitor bank. It is possible to use the DC source to charge the DC capacitor prior to DPT and then disconnect the DC source from the DPT circuit before the test. So what people generally practice, they will charge the capacitor first and then remove the DC source and then they will do the test. So that is also okay, because once the capacitor gets charged, it will supply the energy to the devices. So that is also possible. So the charged DC capacitor can be directly used or recommended for higher voltage to power the DPT circuit. The practice is often preferred for high voltage DPT for safety concern to avoid the need of high voltage DC source. Okay, so we don't have to use too high voltage source, because if we charge the capacitor to its maximum value, then we can use it. So we don't need this value DC source again, right? Up to this point you should be clear that we need the DC source voltage should be higher than the device, which is maximum of the device which is you are using under the test, and about the current we need the minimum current. Okay, now we will move forward again. So now we will see the capacitor. So DC capacitor are there. We have seen in the circuit that there are the two capacitances. So what are the purpose of these two capacitances? So the DC capacitors are employed to maintain a stable DC bus voltage across the phase leads. So first I have told you that from the DC voltage DC source we will charge this capacitor, which is act as our maintain the stable DC bus voltage across the phase leg. So which is act as a bus voltage. One bank of bulk capacitor with large capacitance supplies energy to establish the inductor current during the first pulse. Okay, this thing we have seen. While there is another one capacitor, while the decoupling capacitor with low parasitic equivalent series inductor is responsible for supplying the transient current during the switching transition. So what is the purpose of this decoupling capacitor, which is basically low parasitic equivalent capacitor? So it is responsible for supplying the transient current during the switching transition. So this particular bulk capacitor is called as a C bulk, and the capacitance of the C bulk, energy stored capacity C bulk, is designed to limit the bus voltage variation when the energy transfer from C bulk to load inductor during the first pulse. Okay, so from the during the first pulse only we need this capacitance voltage to transfer and charge our and establish the current in the device, right? So what is the value of this capacitance we will take? So it is L into IL square divided by 2K delta V into VDC square. So again the question is what value we should take, whether VDC minimum we will take or VDC maximum we will take. Again IL minimum we will take or IL maximum we will take. So this thing I will tell you while solving the problem. Okay, so this thing you know. So this is the formula we will use to calculate the value of the C bulk which we are using in our DPT circuit. And one more thing, what is a KdV? So KdV is a voltage variation percentage, which is practically selected as 1 to 5%. Okay, so either you can send 1%, 2%, that is also fine. And what is the value of the decoupling capacitor we will take? So decoupling capacitor is we considered as 100 times the COSS. So what is COSS? We have seen COSS is a output capacitance. So that is also mentioned in the data sheet of the any device. What is its input capacitance? What is its output capacitance? So while selecting the C decoupling capacitor, we should take it as greater than 100 times the COSS. Okay. So till this point, I hope so you have clear how to design the basically supply voltage, inductor and the DC capacitance value. Now we will move forward and we will see another few things how to design. Now moving forward. So now what is the bleeder resistance value we should take? Okay, so because bleeder resistance is also very important thing in our double pulse test circuit. So there are the two criteria while designing the basically bleeder resistance. So what theory is written and two criteria we will see. So the bleeder resistance is introduced across the DC bus we have seen in the circuit to dissipate the remaining energy stored in the DC capacitor and output capacitance of the DC source after the DPT. Okay, so this resistance is used to dissipate the remaining energy stored in the DC capacitor. So while designing this bleeder resistance, there are the two design criteria which we have to look. What is the first designing criteria? The power dissipation of the bleeder resistance during the DPT should be reasonably small, and practically a few watts of power are accepted. So how we can design the DPT? Consider basically a 10 kilo ohm or resistance or something, and we have our maximum voltage across the device. Then from that we can calculate how much power it will dissipate, and similarly we can vary it and we can achieve a very less. We know the relation between the power, voltage and resistance. Power is equals to the V square by R. So we can vary R. We have V maximum as fixed, and we can vary the R, and based on that we can calculate the power, right? So we can get to know that, okay, how this with this particular resistance in this circuit, this much of power is dissipated. Okay, second criteria is the remaining DC capacitor energy released after the DPT should be adequately quick, and practically a discharge time constant of tens of seconds. So 10 of second, not in millisecond we require, tens of second is enough. 10 second, 20 seconds of time is okay, is reasonable. Based on the trade-off between the less power loss and fast discharging time, the bleeder resistance can be selected. So basically we have to maintain the time constant also. Basically fast time constant or slow time constant, how we have to discharge our capacitance, that is in our hand. And second one is how much energy loss we are afford, that is also in our hand. Based on this two parameter we will select our bleeder resistance, and how to take this value we will see in the numerical. Then last thing is the DPT control. So we know that basically we are going to apply the three pulses. One is a turn on pulse, another is a turn off pulse, and third one is again the turn on pulse. Okay, so what duration should we choose for these three pulses? Okay, so based on the DPT operation which we have learned, the three interval T1, T2 and T3 need to be determined. So how and what value of we should take? So generally T1 should be taken as L into IL VDC, T2 should be greater than T off maximum, and T3 should be greater than T on maximum. These two parameter you will get in the data sheet, but practically this T2 and T3 are said to be 1 to 2 microseconds. So you can choose it as 1 microsecond, 2 microsecond, T2 and T3, but T1 you should use this formula L into IL by VDC. Okay, so with this I am concluding the theory part, and we will now see the designing problem. So how you can design? So this is the data which we have available. So the silicon carbide MOSFET from the Wolfspeed is used to illustrate the design and implementation of double pulse test, key component and control. Table below shows the summarize the basic information and desired testing condition for device under test. This design method can be applicable for the other wide bandgap devices also, including the GaN HEMTs and high voltage greater than 3.3 silicon cold devices. Okay, silicon carbide devices. So whatever the data I need from the data sheet, this only data I have taken here, and with this we will design. So what data they have given, that is vendor and model name, breakdown voltage they have given. So this device has a breakdown voltage up to the 1200 volts. So rated current in the device is 24 ampere at 100 degrees Celsius. What is the maximum switching frequency this device can operate? It is a 50 nanosecond. Output capacitance of the device is 80 picofarad. Then testing voltage range they have given. So you can test this between the V minimum is 200 and V maximum is 800. This data is also provided 200 to 800. So this is my maximum, this is my 200 is minimum. Then test current is minimum current is 5 and maximum current is 24. So now we will start with this data, we will start designing the our double pulse test circuit. Okay, so initially we will design the load inductance. So you should keep the two things in mind. When you design the load inductance, you have to take VDC maximum and IL minimum. Okay, we know what is the formula, right? So what we have to take, I told you now what value we should take for VDC and IL, whether it is a minimum or maximum. So you have now come to know that VDC maximum we have to take and IL minimum we have to take. Okay, and we have TSW maximum which is given 50 nanosecond, and I have considered the K delta as 2.5%. Anything you can consider. So just what is important here, VDC maximum we have to take and IL minimum I have to take. Now with this, if I put the values here, I am come to know that my inductance value is 320 micro Henry. Okay, 320 micro Henry is my inductance value. Now again important thing, if you are practically selecting the inductance, then how you have to design, you know, come to know that L value is 320 micro Henry. With greater than 320 micro Henry up to 400 micro Henry I can choose. But for this inductor, what should be the my IL and VDC? For designing purpose I have considered the VDC maximum and IL minimum. But when we practically buy any inductor with this value, I have to take IL maximum and VDC maximum. This thing also you have to take into your mind, that I have to take IL maximum and VDC maximum. So this is important. Okay, so what value we should take and all. So you have understood. I just clearly say one time what we have done. When we design the value of L, we have taken the VDC maximum and IL minimum. But once the value of the L we got, after that what we have done, we have chosen the practical, we have purchased the value, we have purchased the inductor with the maximum inductor current and maximum IL and maximum VDC. So this is thing I wanted to say to you about the inductance. Now we will go to the next part. So this is the basically thing which are showing here. So total inductance value is nearly 400 micro Henry. Okay, so this is how you can choose any inductor. So just I have just which core and all you can choose. So only important thing is we have to see with this parameter which value of the inductor we should take. Okay, now we will see the DC source. So DC supply I already told you. So VDC source should be greater than or equal to VDC maximum. So VDC maximum is 800. So you can take higher than this. So we can take 1000 volt. Okay, so we can take that. So select the DC power source that discussed, we have already discussed, which is always should be greater than, and it's a current range, it should be the minimum. Okay, so it's a current output range I have taken as 0 to 1.5 ampere, that is fine, and 0 to 1000 volt, which is my output voltage of the DC source. So this is the Magnus power, one vendor and model name is given. So this is how you can choose your DC source, right? And why very less current? Because I have told you that we will use to charge the capacitor only, and then we can remove the DC source. So we don't need too much of current capacity, right? Out voltage capacity, it always should be greater than VDC max, right? So this thing we have seen. Then a DC capacitor bank. So how to determine? So two capacitances are there. So how to take? So I have told you, we know the formula for capacitance C bulk, how to calculate, what is the formula, right? But I have told you that what value we should take, VDC and for this. So keep the thing in your mind that we will take VDC minimum and IL maximum. Okay, so what I have said, we have to take VDC minimum and IL maximum. Just keep this thing in your mind. And I have assumed here the percentage variation as 3%. I have just put the value. So L into IL maximum square divided by 2 into kV into VDC minimum. And based on that, I have calculated the C bulk value. It is near becoming 96 picofarad, microfarad, 96 microfarad, right? So this is how we calculate the things. Okay, so in inductor we have taken the VDC maximum and IL minimum, but in capacitance calculation what we have done, VDC minimum and IL maximum. Okay, and we have just put the values and we have calculated the C bulk. Now one more thing we have to see is the DEC. What is DEC? Our decoupling capacitor. So I have told you that it should be greater than 100 times the COS, output capacitance. And in the problem, design problem, they have mentioned that it is what is the value of COS. So based on that, I have taken the value of C decoupling, that is 8 nanofarad. Now what is the voltage level we should take for the decoupling capacitance? So it should be VDC maximum. So what is VDC maximum? We have 800 volts. So accordingly we have taken this particular thing. Okay, so this thing is also, you know, right? Now in summary, if I wanted to buy the capacitor, how should I buy? So I need I have taken to 200 microfarads, like 450 volt metallic polypropylene film capacitor, 2C capacitor in the series. So my requirement is about how many? 96 microfarad. So if I consider the 200 microfarad 2 capacitor in the series, it will be nearly 100 microfarad. So that is fine for me. And my decoupling capacitor I am taking 3.3 nanofarad, 3 capacitor in the parallel. So in parallel if I take, it will nearly the 10, greater than nearly the 10. So my requirement is about 8 nanofarad, so I am taking it as 10 nanofarad. So that is fine. So this is how we will place the capacitor either in the series and parallel, and we make the necessary arrangement for us, right? And these are the just vendor and model name. So you can just go and download this data sheet so that you can come to know in bit more detail about this capacitance and all, right? Now next thing is bleeder resistance. I told you the two criteria while selecting the bleeder resistance. So determine the maximum testing voltage, VDC maximum we know 800 volt. Now choose some particular value of R bleeder. I have considered the 180 kilo ohm, and based on this 180 kilo ohm and maximum VDC max, I have calculated the power dissipated in the resistance. So it is come to be 3.56 watt. So which is very less power. So I am okay with this bleeder resistance. Okay. With the power, the first criteria is okay because I am getting very less dissipation of the power. But second criteria is also important, that its time constant should be 10 second to 20 second it should be. So discharging time constant determine the bleeder resistance DT energy source. So R bleeder into, you know, tau equal to RC. So R bleeder into the C bulk I just have done. So it is 180 into 10 raised to the power 3 and into 100 into raised to the power minus 6. So it is coming nearly 18 seconds. So which is fine. So I can choose this value of the R bleeder for my device and for my circuit, for my double pulse circuit. So this is okay for me. So this is how we have calculated the 4 parameters so far. So in physical I can use the same kind of things. So 2 bleeder resistance in series, each resistor parallel with one of the energy storing capacitor. So this is how we can make the combination and we can proceed further. Okay. So what is value you come to know. Okay. So what value we need? 180. So 180 I have considered 360 kilo ohm to capacitor. Okay. So this is how we can distribute the power loss also, and we can proceed further. Now the last part is the double pulse test control. So what is the value of the T1, T2, T3 we will consider. So it should be taken with the IL by VDC, L into IL by VDC is there now. So what value we have to take? So VDC maximum and IL maximum. So the first pulse which we will give, that is the T1, that is calculated based on the VDC maximum and IL maximum. So we have this two value. I have just put up the value there, T1 equal to L, IL by VDC, T2 I have calculated and T3 I have calculated. Okay. So with this we have calculated the T1, T2, T3 also, and we can generate the pulse and give to our setup, right? So this is how it is shown. So double pulse control signal based on microcontroller. So this is how we will give. This is 12.11 microsecond. So this is how we will generate and we will give to our system. So with this I conclude this lecture. So thanks for watching. I guess you have learned how to design the circuit for double pulse test. So if you have any device now, just download any data sheet and find out its minimum maximum voltage, minimum maximum current, what is its output capacitance, what up to what particular switching frequency this device can be operated. Just download the data, just download the things and just note it down and try to find out all these things. So once you make the circuit with your own and try to find out its value, then you will be in good position that you will come to know, okay, so this is how we will design any double pulse test circuit. So and what are its important component. Okay, just try once, 2 times, practice it, so you will easily understand. So thanks for watching. So these are the references which you can use, and with this I'll conclude this lecture, and in the next lecture we will see few more things of the characterization. So thanks for watching.